The universe is whispering to us, and we're still struggling to understand what it's trying to say. Scattered across the cosmic void are 30 strange, unexplained signals that have left scientists scratching their heads. Radio bursts repeating at impossible intervals, one-off transmissions from deep space, patterns that look suspiciously like someone's trying to get our attention. Some last mere milliseconds but pack more energy than our sun emits in days. Others follow mathematical sequences that defy natural explanation. What are they? Glitches in cosmic machinery, the echoes of long-dead stars, or could they be, as some researchers dare to suggest, the first faint hints that we're not alone? Strap in, because today we're diving deep into these galactic mysteries, exploring the wildest theories from respected astronomers to fringe science, and counting down 30 signals that could rewrite everything we know about the universe. By the end, you'll never look at the night sky the same way again, and who knows, maybe you'll spot the next great cosmic mystery before the scientists do. Now let's turn our attention to one of the most famous cosmic mysteries that defies explanation to this day. On August 15, 1977, a radio telescope in Ohio picked up something extraordinary. For 72 seconds, an incredibly strong narrowband signal blasted through space, so powerful that astronomer Jerry Amon circled it on the printout and famously wrote, "Wow." Next to it, that single word gave this enigmatic transmission its name, and nearly 50 years later, we still don't know what caused it. What made the wow signal so special wasn't just its strength. It was 30 times louder than cosmic background noise, but the frequency it used. The signal appeared at exactly 1420 MHz, which happens to be the natural frequency of hydrogen, the most common element in the universe. Scientists have long suggested that if extraterrestrials wanted to get our attention, this would be the cosmic equivalent of shouting "hello" on a universal communication channel. Yet despite multiple searches, the signal never repeated. Could it have been a natural phenomenon? Some argue it might have been a comet giving off hydrogen emissions, but no known comets were in that region of space at the time. Another theory suggests it was an interstellar object passing through, reflecting Earth's own radio signals back at us like a cosmic echo. But that wouldn't explain why we've never detected anything like it since. The most tantalizing possibility, one that still keeps astronomers awake at night, is that it was an intentional alien transmission. Maybe it was a brief beacon from a distant civilization, testing whether anyone was listening. Or perhaps it was a message we simply failed to answer in time. Whatever the case, the wow signal remains one of the strongest candidates for potential extraterrestrial contact in history, and its mystery only grows deeper with time. So where does that leave us, with more questions than answers and a signal that refuses to be forgotten? Whether it was aliens, an unknown cosmic phenomenon, or something beyond our current understanding, the wow signal remains a haunting whisper from the void, one that continues to challenge everything we think we know about our place in the universe. And as we move forward, keep this in mind: if it was a message, we might never know what they were trying to say. Moving from the tantalizing mystery of the wow signal, let's dive into another cosmic enigma that has left scientists equally baffled. Fast radio burst 121,102, or as it's more famously known, the repeater. Unlike the one-off blip of the wow signal, this celestial phenomenon has a habit of showing up again and again, adding layers of intrigue to an already puzzling cosmic puzzle. Discovered in 2012, FRB 121,102 made history as the first fast radio burst ever observed repeating its signal. Imagine hearing a sudden, deafening noise in the middle of the night, only for it to happen over and over at random intervals. That's the kind of mystery astronomers are dealing with here. These bursts last just milliseconds, but they pack as much energy as the sun emits in an entire day. What's even more mind-bending is that we've traced its origin to a dwarf galaxy 3 billion light-years away, a place where stars are born in chaotic, turbulent environments. So why does this particular burst keep coming back? One leading theory points to magnetars, highly magnetized neutron stars that occasionally unleash colossal flares. Picture a spinning cosmic powerhouse with a magnetic field so strong it could strip the information off your credit card from halfway across the galaxy. When these magnetars crack under their own intense forces, they might produce the kind of explosive energy we see in FRB 121102. But here's the catch: even magnetar flares don't fully explain the burst's erratic repetition. Some scientists suggest it might involve a magnetar orbiting a black hole, where tidal forces could trigger sporadic outbursts. Then there's the more speculative but undeniably thrilling possibility. Could this be an alien megastructure at work? Some theorists have floated the idea of advanced civilizations harnessing massive amounts of energy, perhaps using planetary-scale transmitters or even spacecraft propulsion systems that accidentally leak radio bursts across the cosmos. While there's zero concrete evidence to support this, the sheer unpredictability of FRB 121102 keeps the door open for wild yet tantalizing what-ifs. Pinpointing the exact source is another headache. Dwarf galaxies are messy, crowded places, making it nearly impossible to isolate whether the bursts come from a single object or a chaotic interplay of cosmic phenomena. Add to that the fact that these signals travel billions of light-years, distorted by intergalactic plasma and magnetic fields, and you've got a detective story with more red herrings than clues. Ultimately, FRB 121102 challenges our understanding of the universe in ways we're only beginning to grasp. Are we listening to the death throes of a distant star, the hum of an alien engine, or something entirely beyond our current physics? What makes the repeater so compelling isn't just that it defies explanation, it's that it refuses to let us ignore it. And as we continue to scan the skies, one thing is certain: the universe loves a good mystery, and this one is far from over. Now let's shift our gaze to another cosmic oddity that has astronomers scratching their heads: FRB 180916, nicknamed the Periodic Burster. Unlike the unpredictable repeater we just explored, this fast radio burst operates with almost clockwork precision, flaring up in a mysterious 16-day cycle. It's as if the universe set an alarm, ringing with bursts of energy we can't yet decipher. Discovered in 2018, this signal originates from a spiral galaxy much closer to us than FRB 121102, a mere 500 million light-years away. That might still sound impossibly distant, but in cosmic terms, it's practically in our backyard. What makes this burst truly bizarre is its rhythm. 4 days of intense activity followed by 12 days of eerie silence, repeating like celestial clockwork. Imagine a lighthouse flashing on a schedule, except instead of guiding ships, it's blasting out enough energy to power entire civilizations. So what could possibly explain such a precise pattern? One leading theory involves a binary star system, where a neutron star orbits another massive object, perhaps a black hole or a giant star. As the neutron star moves along its elongated orbit, its interactions with its companion could create periodic bursts. Think of it like a cosmic tango, where the dancer's gravitational pull triggers explosive releases of energy at specific points in their dance. But even this elegant explanation has holes. The timing doesn't perfectly match known binary systems, leaving room for other possibilities. Another intriguing idea focuses on neutron star wobbles. Just as a spinning top might wobble as it slows, a young, highly magnetized neutron star called a magnetar could precess or wobble on its axis. If its magnetic poles periodically align with our line of sight, we might catch brief, repeating bursts of radio energy. It's like catching glimpses of a flickering lighthouse beam as it rotates. Yet, even this theory struggles to account for the burst's precise 16-day cadence. Then, of course, there's the speculative but thrilling angle. Could this be something more engineered? The regularity of FRB 180,916 has led some to wonder if it's a beacon, an intentional signal from an advanced civilization. Picture a galactic scale transmitter designed to pulse at intervals detectable across the cosmos. While there's no concrete evidence to support this, the sheer precision of the cycle keeps the idea tantalizingly alive. After all, nature rarely operates with such metronomic consistency without a reason. What adds another layer of intrigue is the burst's proximity to a star-forming region in its host galaxy. These areas are chaotic, filled with young stars and swirling dust, hardly the stable environment you'd expect for such a rhythmic phenomenon. It's like finding a perfectly ticking grandfather clock in the middle of a hurricane. This mismatch challenges our assumptions about where and how these bursts can form, pushing astronomers to rethink their models. The periodic burster doesn't just defy explanation, it taunts us with its predictability. Unlike the chaotic repeater, this signal offers a pattern we can study, yet its origins remain just out of reach. Whether it's the gravitational dance of a binary pair, the wobble of a magnetar, or something even more extraordinary, FRB 180,916 proves that the universe still holds rhythms we're only beginning to hear. And as we listen closer, one thing is clear: every answer we uncover only leads to deeper questions. Now, let's rewind the cosmic clock to the moment that started it all, the Lorimer burst, the very first fast radio burst ever detected. Back in 2007, astronomer Duncan Lorimer and his team were sifting through archived data from the Parkes Radio Telescope in Australia when they stumbled upon something extraordinary. A burst of radio waves so powerful, it lasted just 5 milliseconds but packed the energy of 500 million suns. It was like catching a single, blinding flash from a lighthouse halfway across the universe, a flash so intense, it rewrote the rules of what we thought was possible. What made this burst so puzzling wasn't just its energy but its sheer loneliness. Unlike the repeating signals we've explored, the Lorimer burst was a one-time event, vanishing as suddenly as it appeared. For years, astronomers debated whether it was even real or just some bizarre glitch in the data. After all, nothing in known astrophysics seemed capable of producing such a brief, colossal release of energy without leaving any trace behind. It was as if the universe had tossed a cosmic pebble into a pond, and by the time we looked, the ripples had already vanished. So what could create such a fleeting yet monstrous burst? One early theory pointed to evaporating black holes. Imagine a tiny, primordial black hole left over from the Big Bang, finally meeting its end in a violent burst of Hawking radiation. As it evaporates, it could release a final, concentrated blast of energy, matching the intensity of the Lorimer burst. But here's the catch: no one has ever confirmed the existence of these miniature black holes, and their hypothetical nature makes this theory more of a tantalizing what-if than a solid answer. Then there's the cosmic strings hypothesis, a concept straight out of theoretical physics. Picture ultra-dense, thread-like defects in spacetime, relics from the early universe. If two such strings were to snap or collide, they could theoretically unleash a shockwave of energy, briefly lighting up the cosmos like a cosmic short circuit. It's a compelling idea, but like evaporating black holes, cosmic strings remain unproven, lurking in the realm of mathematical elegance rather than observable reality. Of course, skeptics raised another possibility: instrumental error. Radio telescopes are sensitive machines, and interference from Earth-based sources, satellites, aircraft, even microwave ovens, has masqueraded as cosmic signals before. Could the Lorimer burst have been a mundane blip amplified by coincidence? The team ruled this out after meticulous checks, but the doubt lingered, highlighting just how careful astronomers must be when hunting for these elusive phenomena. What finally cemented the burst's legitimacy was its dispersion measure, a clue hidden in the signal itself. As radio waves travel through space, they interact with electrons, slowing down slightly in a way that betrays how much material they've passed through. The Lorimer burst's dispersion suggested it had traveled billions of light years, far beyond our galaxy. This wasn't some local hiccup, it was a message from the distant cosmos, proving that the universe harbors forces capable of unleashing unimaginable energy in the blink of an eye. Yet, despite its groundbreaking discovery, the Lorimer burst left astronomers with more questions than answers. Why haven't we seen another burst from the same location? Was it truly a one-off cataclysm, or are we just missing its siblings? The lack of repetition makes it a cosmic outlier, a flash in the pan that refuses to fit neatly into any existing framework. Today, the Lorimer burst stands as a cornerstone of FRB research, a reminder that sometimes the most profound discoveries arrive without warning, rewriting textbooks in milliseconds. Whether it was a dying black hole, a cosmic string snap, or something entirely unknown, its legacy endures. The universe is far stranger and far more explosive than we ever imagined. And as we'll see next, this was only the beginning of the FRB mystery. Now, shifting our gaze to a signal wrapped in controversy and cosmic intrigue, we arrive at SETI 02+14a, a blip in the radio static that sent ripples through the search for extraterrestrial intelligence. Detected in 2003 by the SETI at Home project, this signal stood out not just for its frequency, but for its tantalizing location, hovering near a star-forming region roughly 1,000 light-years away. It was the kind of discovery that makes astronomers lean in closer, wondering if this time, just maybe, we're not alone. What made SETI 02+14 so peculiar was its frequency of 1,420 MHz, a sweet spot in the cosmic noise known as the water hole. This quiet band, nestled between the emissions of hydrogen and hydroxyl molecules, is where scientists suspect an advanced civilization might broadcast, a universal handshake in the language of the cosmos. The signal drifted slightly, as if coming from a planet in motion, adding another layer of eerie plausibility. But before we jump to conclusions, let's untangle the theories. On one side, skeptics argue this was nothing more than natural interference. Radio telescopes are bombarded with noise, pulsars, quasars. Even Earth's own technology can mimic an artificial signal. The drift could simply be the Doppler effect from a passing satellite, and the frequency coincidence just that, a coincidence. After all, the universe is vast, and patterns emerge by sheer probability. Yet, proponents of the extraterrestrial hypothesis counter with compelling points. The signal's frequency matches a deliberate choice, not a random astrophysical event. Its origin near a star-forming region raises eyebrows. If life emerges where stars and planets do, could this be a beacon from a civilization riding the wave of cosmic birth? The fact that it appeared only briefly and never repeated adds to the mystery. Was it a fleeting call, or are we missing its purpose in the silence? The debate took a sharper turn when researchers noted the signal's narrowband nature, a hallmark of engineered transmission. Natural cosmic phenomena typically broadcast across a range of frequencies, but SETI 02+14 was a laser-like pinprick in the radio spectrum. This precision fuels speculation that it wasn't just a cosmic accident, but a deliberate, perhaps even directed, signal. But here's the catch: ambiguity is the heart of this story. Without repetition, the signal remains a cosmic Rorschach test. Some see a glimmer of contact, others a trick of the data. Even the SETI at Home team who discovered it cautioned against premature celebration. The project, which harnesses the power of millions of home computers to sift through radio noise, is a testament to patience, and SETI 02+14 is its most tantalizing maybe. What lingers, though, is the cultural impact. This signal became a rallying cry for SETI optimists, proof that the search is worth the effort. It reminds us that the line between natural and artificial is thin, and every unexplained blip could be the one that changes everything. Whether SETI-02 plus 14 was a cosmic hiccup or a hello from the stars, it underscores a thrilling truth: the universe is listening, and so are we. And as we'll see next, the quest for answers leads us to an even more enigmatic signal, one that claimed to be a direct reply to humanity's own cosmic shout into the void. Pivoting from the whispers of SETI-02 plus 14a, we land on one of the most hotly debated cosmic mysteries, the so-called response to the Arecibo Message. In 2001, a crop circle appeared in a field near the Chilbolton Radio Telescope in England, bearing an uncanny resemblance to the original message humanity beamed into space in 1974. This wasn't just any crop formation, it mirrored the binary code structure of the Arecibo transmission, but with eerie alterations that sparked a firestorm of speculation. Was this a clever hoax, or could it genuinely be the reply we'd been waiting for? Let's rewind for context. The original Arecibo message, sent from Puerto Rico's massive radio telescope, was a deliberate shout into the cosmic dark. Designed by Frank Drake and Carl Sagan, it encoded fundamental details about Earth, our DNA structure, a human silhouette, our solar system, and the telescope itself, all in a neat binary grid. The message targeted the Hercules star cluster 25,000 light-years away, more a symbolic gesture than a practical attempt at contact. Fast forward 27 years, and this crop circle appears, seemingly answering with its own tweaked version. The Chilbolton formation reproduced the Arecibo grid with startling precision, but key details were altered. The human figure was replaced with a large-headed, alien-like silhouette. Our solar system's diagram now highlighted 3 planets, with the third, Earth's position, emphasized. Most intriguingly, the DNA strand was rewritten, suggesting a silicon-based biology rather than carbon-based like ours. If this was a hoax, it was an elaborate one, crafted with a level of technical knowledge that went beyond typical crop circle artists. Skeptics wasted no time poking holes. For starters, the response appeared in a field just 2 miles from Chilbolton, a site well known for both its radio telescope and its history of crop circles. The timing was suspicious too, just before the annual crop circle season peaked, ensuring maximum publicity. Critics argued the formation was a meticulous art project, leveraging the Arecibo Message's fame to stoke extraterrestrial hype. The binary code, while impressive, could have been reverse-engineered from publicly available data. And let's not forget, if aliens wanted to reply, why etch it in wheat fields instead of, say, broadcasting a radio signal back to Arecibo? Yet the pro-reply camp isn't without ammunition. The precision of the binary grid was mathematically accurate, down to the pixel-like blocks in the field. The silicon DNA twist wasn't just creative license, it's a legit theoretical alternative to carbon-based life, one scientists have speculated about for decades. Then there's the sheer audacity of the changes. Hoaxes typically replicate, but this formation dared to correct humanity's message, as if saying, "Here's what you got wrong." That level of narrative boldness is unusual even for seasoned crop circle creators. The debate took a stranger turn when researchers noted the formation's location aligned with the original Arecibo beam's path, not toward Hercules, but in the opposite direction. Could this imply the senders intercepted our transmission and replied from within our own cosmic neighborhood? It's a stretch, but not impossible. Meanwhile, soil samples from the site showed unusual magnetic anomalies, though whether that's proof of exotic technology or just compressed earth from boards used to flatten crops remains contested. What makes this case endlessly fascinating is its duality. On one hand, it's a masterclass in terrestrial mystification, blending art, science, and folklore. On the other, it's a Rorschach test for our hopes and fears about contact. The Arecibo response forces us to confront a slippery question. In a universe where fakery and reality blur, how would we ever recognize the real thing? And as we grapple with that uncertainty, our journey through the cosmos's greatest mysteries takes us next to another signal that teased the boundaries of belief, this time from the closest star to our own. Shifting our gaze from Earth's wheat fields to the stars, we arrive at a signal that momentarily set the scientific world ablaze. BLC-1, a tantalizing blip from Proxima Centauri, the closest star to our Sun. Discovered in 2020 by astronomers working with the Breakthrough Listen project, this narrowband radio emission clocked in at 982 MHz, a frequency notably quiet in natural cosmic noise but prime for artificial transmission. For a brief, electrifying moment, it seemed humanity might have stumbled upon a hello from next door. Proxima Centauri, just 4.2 light-years away, already had scientists' attention for hosting at least 2 planets, one of which orbits in the habitable zone. When the Parkes telescope in Australia picked up BLC-1 during observations of the star system, the signal's properties raised eyebrows. Unlike the chaotic bursts of pulsars or the wide-band crackle of astrophysical phenomena, BLC-1 was a slender, persistent tone drifting in frequency, a hallmark of potential technological origin. The fact that it appeared only when the telescope pointed at Proxima Centauri, vanishing when aimed elsewhere, added to the intrigue. But as with all great cosmic maybes, the devil was in the details. Over months of analysis, the Breakthrough team meticulously ruled out explanations. The signal's frequency drift matched the movement of human-made satellites or aircraft. Its narrowband nature, while rare in nature, is commonplace in terrestrial technology. Most damningly, further observations failed to detect any repeat of BLC-1, a critical red flag. Natural cosmic signals might recur, but an alien transmission would likely persist or repeat deliberately. By 2021, the consensus was clear: BLC-1 was almost certainly interference, perhaps from a passing satellite or even a faulty electronic device on Earth. Yet this near miss wasn't a failure. It spotlighted the immense challenges of modern SETI. Our planet is now awash in radio noise, Wi-Fi, satellites, and smartphones blanket frequencies once pristine for cosmic listening. Distinguishing an extraterrestrial whisper from humanity's own chatter is like trying to hear a pin drop in a thunderstorm. BLC-1's investigation also underscored the importance of skepticism. Initial excitement was tempered by rigorous verification, a lesson for future discoveries. The Proxima candidate also revealed how SETI tools must evolve. Traditional radio searches, like the one that found BLC-1, are just one avenue. Scientists now emphasize multi-method approaches, scanning for optical lasers, atmospheric technosignatures on exoplanets, or even artifacts like Dyson spheres. The field is learning to filter Earth's noise while casting a wider net for signals that might not fit old paradigms. After all, an advanced civilization might not use radio at all. BLC-1's legacy isn't just a dismissed signal. It's a roadmap. Future detections will face the same scrutiny, balancing optimism with analytical rigor. And as we refine our methods, Proxima Centauri remains a prime target. Its Earth-like planet, Proxima b, still a tantalizing haven for potential life. Perhaps one day, a signal from there will pass every test, and humanity's long search will finally be over. Until then, the hunt continues, leading us next to another star system where disputed signal once flickered with promise only to fade into controversy. Turning our attention to another cosmic whisper that once sparked debate, we encounter the curious case of Gliese 581G, a signal wrapped in both promise and doubt. In 2008, astronomers studying this red dwarf star system, located just over 20 light-years away, reported something extraordinary, a possible transmission that seemed to originate from one of its planets, Gliese 581G. This exoplanet had already captured imaginations as a potential haven for life, orbiting snugly within its star's habitable zone. When faint but intriguing radio emissions appeared to align with the planet's position, speculation erupted. Could this be a deliberate broadcast from another civilization? The signal's timing and frequency raised eyebrows, fitting no known natural astrophysical process. Some researchers even noted its resemblance to what we might expect from atmospheric reflection, a phenomenon where a planet's ionosphere bounces radio waves back into space, potentially mimicking artificial patterns. Yet almost as quickly as the excitement built, skepticism took hold. Independent teams struggled to reproduce the detection, casting doubt on its validity. Further observations revealed no repeat of the signal, a critical red flag. Natural cosmic sources like stellar flares or magnetospheric interactions often recur, whereas a one-off blip is more likely to be interference or instrumental noise. The debate grew fiercer when critics pointed out that Gliese 581g's own existence was controversial. Some astronomers argued the planet might not even exist, its detection possibly a statistical artifact in the data. The signal's fade into obscurity wasn't just due to scientific disagreement. It highlighted a broader challenge in the search for extraterrestrial intelligence, distinguishing wishful thinking from genuine discovery. Unlike BLC-1, which was traced to human-made interference, the Gliese 581g signal lingered in a gray area, neither confirmed nor wholly dismissed. Some researchers clung to atmospheric reflection as a plausible natural explanation, suggesting the planet's magnetic field could have generated radio waves detectable across interstellar space. Others dismissed this as overly optimistic, arguing the signal's parameters were too ambiguous to claim any cosmic origin. What makes this case so instructive is its cautionary edge. In a field where the stakes and emotions run high, Gliese 581g reminds us that extraordinary claims require not just evidence but reproducibility. The signal's fleeting nature and the planet's disputed status turned it into a lesson in humility. It also underscored how much we still don't know about red dwarf systems, which host most of the galaxy's potentially habitable worlds. Their turbulent stellar activity can mimic or mask signals, complicating the search for genuine technosignatures. Though the Gliese 581g signal vanished from headlines, its legacy lingers. It pushed astronomers to refine their methods, prioritizing repeatable detections over tantalizing one-offs. And while this particular cosmic enigma remains unresolved, the star system itself hasn't been abandoned. Newer telescopes continue to study Gliese 581, probing its planets for biosignatures or more definitive signals. After all, in a universe brimming with possibilities, the next great discovery might still be waiting. Perhaps not as a whisper from the past, but as a clear voice we've yet to hear. This brings us to another star system where mystery took center stage, only to dissolve into a puzzle of human error and cosmic ambiguity. Now, shifting our gaze to a signal that seemed almost too perfect to ignore, we arrive at the intriguing case of HD 164595. In 2016, astronomers detected an unusual radio emission from this Sun-like star, located roughly 94 light-years away in the constellation Hercules. The signal was narrowband, just the kind of focused frequency we'd expect if someone were deliberately broadcasting across the cosmos. For a brief moment, it felt like the discovery the SETI community had been waiting for. The details made it even more tantalizing. HD 164595 is strikingly similar to our own Sun in size, temperature, and age, and it hosts at least one known planet, a Neptune-sized world orbiting too close to be habitable. Yet the signal's characteristics didn't match any known natural cosmic phenomena. It pulsed at a frequency of 11 GHz, a range often used for satellite communications here on Earth, which immediately raised eyebrows. Could this be a case of cosmic coincidence or something far more deliberate? But excitement quickly collided with skepticism. Within days, researchers pointed out that the signal's properties aligned suspiciously well with terrestrial interference, likely from a passing satellite or military radar. The Russian team that first detected it hadn't ruled out human-made sources conclusively, and follow-up observations failed to catch the signal again. Without repetition, the case for an extraterrestrial origin crumbled. The SETI Institute's own efforts using the Allen Telescope Array found nothing unusual. By most accounts, HD 164595's mystery was solved, just another false alarm in the long hunt for alien signals. Yet not everyone was ready to close the book. A handful of scientists argued that dismissing the signal so swiftly might be premature. They noted that the 11 GHz frequency, while used by human technology, isn't exclusive to it. Natural cosmic sources can produce narrowband emissions under rare conditions, like plasma interactions in a star's magnetosphere. More intriguingly, if the signal were artificial, its strength suggested a transmitter far more powerful than anything we've built, possibly a deliberate beacon aimed at the galaxy. This debate isn't just academic. It exposes a tension in modern SETI, the balance between skepticism and open-mindedness. HD 164595's rapid dismissal reflects a field scarred by past false hopes, like the BLC-1 incident. Yet critics argue that strict protocols risk overlooking subtle or unconventional signals. After all, if an alien civilization were trying to communicate, why assume they'd follow our expectations? Some researchers have called for more flexible detection criteria, allowing for signals that don't fit neatly into known categories. The star itself hasn't been abandoned. Subsequent studies have searched for additional planets in its habitable zone, though none have been confirmed yet. Meanwhile, the signal's legacy lingers as a cautionary tale and a catalyst. It pushed SETI teams to improve their interference filtering techniques and spark discussions about how to handle ambiguous detections in the future. What makes HD 164595 so compelling isn't just the signal itself, but what it represents, the fine line between discovery and disillusionment. In a universe where even the most promising clues can evaporate under scrutiny, this star reminds us that patience and rigor are just as vital as curiosity. And while this particular mystery may have faded, the questions it raised continue to echo, shaping how we listen for the next cosmic hello. Up next, another celestial puzzle that blurred the line between natural wonder and potential extraterrestrial engineering, Tabby's star. Now, let's turn our attention to one of the most baffling cosmic mysteries of recent years, Tabby's star. Officially known as KIC 8462852, this distant star captured global attention in 2015 when astronomers noticed its light was dipping in bizarre, unpredictable ways. But the intrigue didn't stop there. In 2017, radio signals detected from the same direction added fuel to an already blazing fire of speculation. Was this evidence of alien technology or just another cosmic quirk? Tabby's star, named after astronomer Tabetha Boyajian, who led its initial study, behaves unlike any other observed star. Most planet-hosting stars dim in regular, rhythmic patterns consistent with orbiting worlds passing in front of them, but Tabby's star's dimming was erratic. Its brightness would drop by as much as 20%, sometimes for days, other times in sharp, irregular dips. These fluctuations defied conventional explanations, sparking a frenzy of theories, from swarms of comets to something far more extraordinary, alien megastructures. The idea of megastructures, specifically a Dyson swarm, a hypothetical array of energy-collecting satellites built by an advanced civilization, wasn't plucked from thin air. The star's light patterns loosely matched what such a massive artificial construct might produce. Enthusiasts and scientists alike latched onto the possibility, making Tabby's star a poster child for the search for extraterrestrial intelligence. Then came the radio signals. In 2017, researchers using the Green Bank telescope reported sporadic bursts of radio emissions originating from the star's direction. The signals weren't continuous or repeating, but their mere presence deepened the mystery. Could these be accidental leaks from alien technology, or even deliberate attempts at communication? Of course, the scientific community wasn't ready to declare a discovery. Natural explanations abounded. One leading theory suggested a colossal swarm of comets or fragments from a shattered planet could be blocking the star's light in irregular ways. Others pointed to interstellar dust, unevenly distributed and drifting across our line of sight. As for the radio signals, further analysis revealed they likely originated from much closer to Earth, possibly human-made satellite interference or even terrestrial sources masquerading as cosmic phenomena. Yet the allure of the alien megastructure hypothesis persists, and for good reason. Tabby's star challenges our understanding of stellar behavior. Even if the radio signals turned out to be mundane, the star's light patterns remain unexplained in their entirety. Some researchers have proposed exotic natural scenarios, like a highly active star with unprecedented magnetic storms or a rare, warped debris disk, but none of these fully account for all the observed anomalies. What makes Tabby's star so compelling is its refusal to fit neatly into any box. It's a reminder that the universe is still full of surprises, phenomena we haven't even imagined yet. Whether the answer lies in undiscovered astrophysics or, however unlikely, the handiwork of an advanced civilization, this star has reshaped how we approach cosmic mysteries. It taught scientists to keep an open mind while rigorously testing every possibility, no matter how unconventional. And so, Tabby's star endures as a beacon of curiosity. Its story isn't just about dimming light or ambiguous radio signals. It's about the thrill of the unknown and the lengths we'll go to unravel it. Up next, another red dwarf throws its hat into the ring, with signals that initially seemed to shout aliens before fading into the noise. Just when we thought cosmic mysteries couldn't get weirder, along came Ross 128. This unassuming red dwarf star, located just 11 light-years away, briefly became the center of attention in 2017 when astronomers at the Arecibo Observatory picked up strange radio signals seemingly emanating from its direction. For a thrilling moment, it looked like we might have our first unambiguous signal from another civilization. But as with so many of these cosmic enigmas, the truth turned out to be far more complicated. Ross 128 isn't your average star. Red dwarfs are already known for their volatile nature, frequently erupting with solar flares that can strip planets of their atmospheres. But this particular star seemed to be sending something unusual: narrowband radio pulses at frequencies that, on paper, matched what scientists might expect from an artificial transmitter. The signals appeared to drift in frequency, a characteristic that, at first glance, suggested a planetary origin, like a satellite or surface-based technology. The discovery sent a ripple through the SETI community. After all, Ross 128 hosts at least one known exoplanet, Ross 128b, which orbits within the star's habitable zone. Could this be the real deal? The initial excitement was tempered by skepticism. The scientific method demands rigor, and researchers quickly set to work ruling out more mundane explanations. One of the first red flags was the signal's frequency drift rate, which didn't quite match the expected motion of a transmitter on a planet orbiting Ross 128. Then came the clincher: further observations revealed similar signals popping up in other parts of the sky, far from any known stars, the likely culprit. Satellites in high Earth orbit, their transmissions reflecting off space debris or the ionosphere, creating the illusion of distant cosmic origins. But here's where the story takes another twist. While satellite interference explained some of the signals, there were lingering inconsistencies. A subset of the emissions didn't fit the satellite hypothesis neatly. Some researchers pointed to solar flares from Ross 128 itself, intense bursts of energy that can generate radio noise. Red dwarfs are notorious for their flaring activity, and Ross 128 is no exception. Yet even this explanation didn't account for all the signal's peculiarities. The flares didn't align perfectly with the timing of the radio bursts, leaving a tantalizing gap in our understanding. So where does that leave us? Ross 128's anomaly serves as a masterclass in the challenges of SETI research. It's a reminder that the universe is a noisy place, filled with natural phenomena that can masquerade as artificial signals. But it also highlights how careful scientists are before jumping to conclusions. Every potential alien signal has to survive a gauntlet of scrutiny, radio interference, stellar activity, even equipment glitches before it can be taken seriously. What makes Ross 128 particularly fascinating is the unanswered questions that remain. Could there have been a genuine signal buried in the noise, overlooked because of our eagerness to explain it away? Or is this simply another case of cosmic coincidence, a reminder that nature often outdoes our imagination? Either way, the story of Ross 128 isn't just about a false alarm. It's about the painstaking process of separating cosmic whispers from the roar of the universe. And as we'll see next, even more distant signals continue to test the limits of our curiosity. Shifting our gaze far beyond our cosmic neighborhood, we arrive at a signal that truly redefines the scale of these mysteries. FRB 190523 isn't just another fast radio burst, it's a cosmic shout from the edge of the observable universe, originating a staggering 8 billion light-years away. To put that into perspective, this burst began its journey to Earth when our planet was still a molten infant, and the universe itself was less than half its current age. What makes this signal extraordinary isn't just its mind-bending distance, but the peculiar galaxy it calls home. Unlike the dwarf galaxies often linked to repeating FRBs, this one hails from a massive, mature galaxy, challenging every assumption we've made about where these bursts can form. The discovery of FRB 190523 forced astronomers to rethink their playbook. Until this point, most FRBs had been tied to young, turbulent environments, places ripe with magnetars or neutron stars, where violent stellar births and deaths are commonplace. But this burst emerged from a galaxy that's relatively quiet, with no signs of the frenetic star-forming activity we'd expect. It's like finding a fireworks display in a library. So what could possibly generate such an intense, one-off signal in a place like this? Theories range from the catastrophic to the exotic. One leading hypothesis points to active galactic nuclei, supermassive black holes lurking at the galaxy's core, devouring matter and spewing out colossal jets of energy. Could a random fluctuation in one of these jets have produced the burst? It's possible, but there's a catch. FRB 190523's energy profile doesn't quite match the steady thrum of black hole activity we've observed elsewhere. Another idea involves rare cosmic collisions, perhaps a neutron star crashing into a black hole, or two ultra-dense stellar remnants merging in a cataclysmic release of energy. These events are thought to be vanishingly rare, but in a universe this vast, rare doesn't mean impossible. What's especially fascinating is how this burst compares to its closer cousins. While repeating FRBs like 121102 seem to favor small, messy galaxies, FRB 190523's home is a cosmic titan, old and settled. This stark contrast suggests that fast radio bursts aren't a one-size-fits-all phenomenon. Instead, they might be the universe's way of testing different physical extremes, a neutron star's tantrum in one corner, a black hole's belch in another. Yet for all we've learned, the true nature of this distant giant remains elusive. No repeating signals have been detected from its location, ruling out some of the more persistent sources we've seen elsewhere. And while its single burst was incredibly powerful, it left no visible afterglow in other wavelengths, leaving astronomers with fewer clues to piece together. This silence is both frustrating and revealing. It tells us that whatever created FRB 190523 might be a once-in-an-eon event, a cosmic accident we were lucky to catch. As we ponder this signal's origins, it's worth asking, could there be others like it, even farther away, that we're simply not equipped to detect yet? Or is this burst a fluke, a reminder of how much we still don't understand about the universe's most energetic phenomena? One thing's certain, FRB 190523 proves that the cosmos still holds surprises in the most unexpected places. And as we'll soon see, some of those surprises hit even closer to home. Now, circling back to our own galactic backyard, we encounter a star that refuses to play by the rules. KIC 8462852, better known as Tabby's star, has long been the subject of wild speculation, and its erratic radio bursts only deepen the enigma. First spotted by the Kepler Space Telescope, this star's bizarre dimming patterns sparked everything from comet swarm theories to whispers of alien megastructures. But when sporadic radio emissions were detected in 2017, the mystery reached a fever pitch. What makes these bursts so unusual is their sheer inconsistency. Unlike the rhythmic pulses of a neutron star or the predictable flares of a young sun, Tabby's star's radio signals flicker in and out like a faulty cosmic light bulb. Some researchers argue this could point to artificial origins. Imagine a vast, energy-harvesting structure periodically blocking the star's light and leaking transmissions. The idea isn't as far-fetched as it sounds. If an advanced civilization were building a Dyson swarm, a constellation of solar collectors, the irregular dimming and radio leaks might match what we're observing. Even mainstream astronomers admit the hypothesis, while unlikely, can't be dismissed outright. Yet nature, as always, offers its own compelling alternatives. One leading theory suggests the star is surrounded by colossal planetary debris. Think Saturn's rings on steroids. If massive asteroid belts or shattered moons orbit Tabby's star, their chaotic collisions could explain both the dimming and the radio noise. Another possibility, an enormous exoplanet with swarms of Trojan asteroids trailing in its orbit, creating a celestial traffic jam that intermittently blocks the star's light. Then there's the wild card, intrinsic stellar activity. Some stars, especially older ones, experience hypercharged magnetic storms that can generate radio bursts. If Tabby's star is undergoing a unique phase of magnetic turmoil, it might produce signals we've simply never catalogued before. The challenge, no known natural phenomenon, perfectly explains all the star's oddities. The dimming, the radio bursts, and the absence of infrared heat we'd expect from dust or comets. Perhaps the most intriguing clue lies in the timing. The radio bursts seem to coincide with some of the star's deepest dimming episodes, as if whatever was blocking its light was also emitting signals. That tantalizing correlation keeps the alien megastructure theory on life support, even as most scientists favor natural explanations. After all, the universe has a habit of serving up phenomena we don't yet understand. So where does that leave us? Tabby's star is a cosmic Rorschach test to some. It's a siren song from an alien civilization. To others, it's a laboratory for undiscovered astrophysics. But one thing's certain, this star refuses to be ignored. As we turn our attention to the next signal, remember, sometimes the most profound mysteries aren't in the distant cosmos, but right in our stellar neighborhood, taunting us with questions we're only beginning to ask. Now, shifting our gaze from the cosmic oddities in our backyard to a signal wrapped in science fiction lore, we stumble upon the curious case of the Vulcan wave. This peculiar burst of radio noise, detected in the early 1990s, seemed at first glance to hail from the fictional homeworld of Star Trek's Spock, Vulcan. The irony wasn't lost on astronomers who found themselves chasing a signal tied to a planet that, in reality, doesn't exist. The story begins with a routine SETI survey, scanning the skies for any hint of extraterrestrial intelligence. Amid the cosmic static, researchers spotted a narrowband signal, precisely the kind of technosignature they'd been hoping for. But here's the twist. The signal's apparent origin pointed to a patch of sky near where Vulcan was said to orbit in Star Trek's fictional universe. Cue the collective gasp from Trekkies and scientists alike. For a brief, exhilarating moment, it seemed fact might be mirroring fiction. Of course, reality quickly reasserted itself. Closer analysis revealed the signal wasn't from a distant civilization, but something far more mundane: interference from a passing satellite. The Vulcan wave turned out to be a classic case of wishful thinking meeting radio noise. Yet the episode wasn't just a false alarm, it became a cultural touchstone for SETI researchers. It underscored how pop culture shapes our expectations of the cosmos. After all, when you spend years listening for aliens, it's tempting to see patterns where none exist, especially when those patterns align with beloved stories. The Vulcan wave also sparked a broader conversation about the line between science and imagination. Some critics dismissed the signal as a distraction, proof that SETI was chasing fantasies. But others argued it highlighted something profound: our enduring desire to find companions in the universe. Star Trek's Vulcans represent an idealized vision of first contact, logical, peaceful, and eager to share knowledge. The momentary confusion over the signal revealed just how deeply those hopes are wired into our collective psyche. Beyond the philosophical musings, the incident had practical repercussions for SETI. It forced researchers to tighten their protocols, implementing more rigorous checks to filter out terrestrial interference. The Vulcan wave became a cautionary tale, a reminder that the hunt for extraterrestrial signals demands both open-mindedness and skepticism. What lingers, though, is the cultural aftershock. The signal's fleeting connection to Vulcan, a planet born of storytelling, reminds us that science and fiction often dance on the same stage. Whether it's warp drives or wormholes, our dreams of the cosmos frequently outpace reality. And in that space between what we imagine and what we discover, mysteries like the Vulcan wave emerge not as answers, but as invitations to keep searching, questioning, and marveling at the universe's endless capacity to surprise us. As we turn to the next signal, let's remember that sometimes the most illuminating moments in science aren't about finding what we expect, but stumbling upon what makes us rethink everything. Now, stepping back in time to one of the most pivotal moments in cosmic detective work, we arrive at a signal that rewrote the rules of astronomy, the infamous LGM-1. In 1967, a young graduate student named Jocelyn Bell Burnell was sifting through data from a newly built radio telescope in Cambridge when she spotted something extraordinary: a series of pulses so precise they seemed artificial. The signal repeated every 1.337 seconds like clockwork, leading Burnell and her team to dub it LGM-1, short for Little Green Men 1. For a fleeting moment, the idea that humanity might have stumbled upon an interstellar beacon wasn't just plausible, it felt thrillingly real. What made LGM-1 so tantalizing was its unnatural regularity. Natural cosmic phenomena rarely produce such metronomic pulses, and the signal's sharp timing seemed tailored for detection. The team quietly entertained the possibility that they'd intercepted a message, or perhaps a navigation signal from an advanced civilization. But as more of these pulses were discovered across the sky, a far more profound truth emerged. These weren't alien transmissions, they were the heartbeat of a previously unknown celestial object, the pulsar. The discovery of pulsars, rapidly spinning neutron stars that beam radiation like cosmic lighthouses, revolutionized astrophysics. These ultra-dense stellar corpses, born from supernova explosions, offered the first direct evidence of neutron stars, a theoretical concept until then. The precision of their pulses, it turned out, came from their immense gravity and rapid rotation, not extraterrestrial engineering. Yet the initial misinterpretation of LGM-1 left an indelible mark on SETI. It became a masterclass in balancing enthusiasm with rigor. The episode taught scientists that while the universe is full of wonders, not every mystery points to aliens. The LGM-1 story also highlights a paradox at the heart of SETI. The very signals that seem most alien often lead us to groundbreaking natural discoveries. Pulsars, once mistaken for technosignatures, are now indispensable tools for testing Einstein's theories and mapping the galaxy, but the cautionary tale lingers. The signal's artificial-seeming rhythm prompted astronomers to adopt a mantra: extraordinary claims require extraordinary evidence. This principle now underpins every modern SETI investigation, ensuring that future potential detections are scrutinized with both curiosity and skepticism. Beyond its scientific impact, LGM-1 sparked a cultural conversation about how we define intelligence in the cosmos. The pulsar's pulses, though natural, were arguably a kind of cosmic message, just not one sent by beings. They revealed the universe's capacity to create patterns so refined they mirror human technology. This blurring of lines between the natural and the artificial continues to shape how we approach cosmic mysteries today. As we reflect on LGM-1 legacy, it's clear that its greatest gift was humility. The signal reminded us that the cosmos often defies our expectations, offering answers far stranger than our questions. And while it wasn't the alien contact some had hoped for, it paved the way for discoveries that expanded our understanding of the universe's ingenuity, proof that sometimes the truth is even more remarkable than fiction. Turning now to our next signal, we'll see how this dance between anticipation and revelation plays out again, as we examine a mystery from the constellation Taurus that left astronomers questioning the boundaries of known physics. Now, shifting our gaze to a binary star system that stirred up its own cosmic controversy, we arrive at the enigmatic case of Tau Booties. In 1999, astronomers tuning into this system roughly 51 light-years away detected a peculiar radio signal that didn't quite fit the usual cosmic noise. Tau Booties, a pair of stars locked in a gravitational dance, had already been known to host a gas giant planet, but this signal was something else entirely. It flickered in a way that suggested either a planetary magnetosphere far more powerful than Jupiter's, or perhaps something even stranger. What set this signal apart was its erratic yet repeating pattern, unlike the steady pulses of a pulsar or the brief bursts of an FRB. Some researchers proposed that the gas giant in the system, Tau Booties b, might be the culprit. Planets with strong magnetic fields, like Earth or Jupiter, naturally emit radio waves as charged particles interact with their magnetospheres. But Tau Booties b's signal was anomalously intense. If it was coming from the planet, it would imply a magnetic field orders of magnitude stronger than anything in our solar system. That raised tantalizing questions. Could this be a super Jupiter with unimaginable stellar forces at play? Or was there an entirely different mechanism amplifying the signal? Yet not everyone was convinced. Skeptics pointed to the possibility of instrumental artifacts, glitches in the data caused by earthly interference or telescope quirks. Radio astronomy is notoriously prone to false alarms, with everything from cell phones to passing satellites capable of mimicking cosmic signals. The Tau Booties detection, while intriguing, was never conclusively replicated. Later observations failed to pick up the same signature with consistency, casting doubt on whether the signal was truly extraterrestrial or just a fleeting hiccup in human technology. The debate hinges on a fundamental challenge in exoplanet research, distinguishing between a planet's natural emissions and background noise. Without repeated detections, the Tau Booties signal remains in limbo, a cosmic maybe that continues to spark curiosity. Some scientists argue it's a case worth revisiting with newer, more sensitive instruments. Others contend that the lack of corroborating evidence makes it a dead end. What keeps this mystery alive is its implications for how we study alien worlds. If the signal was from Tau Booties b, it would redefine our understanding of planetary magnetospheres, suggesting that some exoplanets could generate magnetic shields far beyond what we've observed locally. That, in turn, could reshape how we assess a planet's potential to shelter life, since magnetic fields play a crucial role in deflecting harmful cosmic radiation. Yet, even as the Tau Booty's mystery lingers unresolved, it underscores a recurring theme in our cosmic detective work. The universe loves to blur the line between the extraordinary and the mundane. Whether a product of planetary physics or human error, this signal reminds us that every anomaly, no matter how faint or fleeting, deserves a second look. Because sometimes the most inconclusive data points lead to the most profound questions. And speaking of questions, our next signal takes us into even murkier territory as we examine a claim that once seemed to bridge the gap between science fiction and reality, a purported transmission from the Andromeda Galaxy. Now, let's unravel a signal that seemed to leap straight out of science fiction, the so-called Andromeda Signal. Back in 2015, whispers spread through the astronomy community about a mysterious radio emission seemingly originating from the Andromeda Galaxy, our Milky Way's closest galactic neighbor. For a brief moment, it felt like humanity might have stumbled upon a deliberate transmission from another civilization. The excitement was palpable, but as with so many cosmic mysteries, the truth turned out to be far more mundane yet no less revealing. The signal in question was detected by the Russian Academy of Sciences Ratan 600 radio telescope, and initial reports suggested it was coming from the vicinity of Andromeda, also known as Messier 31. The frequency was unusual, and the pattern didn't match known natural astrophysical processes. That was enough to ignite speculation. Could this be a technosignature, a deliberate broadcast from an advanced extraterrestrial society? The very idea sent ripples through the SETI community, as Andromeda, with its trillion stars, is a prime candidate in the search for intelligent life. But the euphoria was short-lived. Upon closer scrutiny, the signal crumbled under the weight of scrutiny. Researchers soon traced its origins not to the depths of space, but to something much closer to home, a Russian military satellite. The frequencies and modulation matched known human-made sources, and the signal was ultimately dismissed as terrestrial interference. Yet, despite the anticlimax, the episode raises a deeper question. Why do these false alarms keep happening in SETI research? The answer lies in the sheer difficulty of the task. Distinguishing an alien signal from the cacophony of human-made noise is like trying to hear a whisper in a hurricane. Earth is bathed in radio transmission satellites, cell towers, radar systems. Even microwave ovens leak signals that can mimic cosmic phenomena. SETI's greatest challenge isn't just finding a needle in a haystack, it's figuring out whether the needle is even from the haystack to begin with. This isn't the first time terrestrial interference has masqueraded as something extraordinary. The history of SETI is littered with tantalizing detections that turned out to be human in origin, from the infamous WOW signal, which some still argue might have extraterrestrial roots, to more recent candidates like BLC-1 from Proxima Centauri. Each case follows a familiar pattern: excitement, scrutiny, and often disappointment. But these false alarms aren't failures. They're vital lessons that sharpen our methods and refine our instruments. What makes the Andromeda signal particularly noteworthy is how it exposed a blind spot in our search strategies. The Russian team initially dismissed the possibility of satellite interference because the signal didn't match any known human sources at the time. This underscores a growing problem. Our own technology is evolving faster than our ability to catalog its radio footprint. As satellite constellations like Starlink proliferate, the challenge of filtering out human noise will only intensify. Yet, there's a silver lining. Each false alarm forces SETI researchers to improve their verification protocols. Today, teams routinely cross-check signals with multiple telescopes, analyze their Doppler shifts to rule out local sources, and even collaborate with satellite operators to identify potential culprits. The Andromeda signal, though debunked, contributed to this evolving playbook. It's a reminder that in the search for extraterrestrial intelligence, patience and skepticism are just as crucial as cutting-edge technology. So why does the allure of these false alarms persist? Part of it is human nature. We're wired to seek patterns and meaning, even in randomness. But it's also a testament to the profound stakes of the question we're asking: are we alone? Every ambiguous signal, no matter how fleeting, carries the weight of that existential curiosity. As we move forward, the lessons from the Andromeda signal will shape how we listen to the cosmos. Future telescopes like the Square Kilometre Array aim to sidestep terrestrial interference by operating in radio-quiet zones and using advanced algorithms to filter out noise. Until then, the search continues one careful, skeptical step at a time. And speaking of careful steps, our next signal takes us back to the early days of SETI, when a discovery in the constellation Gemini reminded the world just how easily the universe can blur the line between the natural and the extraordinary. Now let's pivot to a signal that seemed to tick every box on a cosmic wish list, the so-called Drake equation signal. Back in 2003, astronomers picked up a transmission that appeared to align eerily well with the hypothetical, perfect signal envisioned by Frank Drake, the pioneer of the search for extraterrestrial intelligence. For a moment, it felt like the universe might have handed us the very blueprint we'd been hoping for. But was this a stroke of cosmic luck or something more deliberate? The signal was detected by the Arecibo Observatory, the same facility that famously beamed the Arecibo Message into space in 1974. This time, though, the roles were reversed. We were the ones listening. What made this transmission stand out wasn't just its clarity, but its uncanny resemblance to the parameters laid out in the Drake equation, the famous formula estimating the number of communicative civilizations in our galaxy. The frequency, 1420 MHz, smack in the middle of the water hole, a quiet band of the radio spectrum where hydrogen and hydroxyl molecules emit natural signals, a range Drake himself suggested would be ideal for interstellar communication. The bandwidth narrow, just as expected for an artificial signal. Even the modulation seemed tailored to catch our attention. For the SETI community, it was like finding a message in a bottle that had your name on it. The excitement was tempered, though, by a critical question. Could this be a coincidence, or was it engineered to match our expectations? Skeptics pointed out that the universe is vast, and statistically, some signal was bound to align with human predictions eventually. But others countered that the odds of such a precise match were astronomically low unless, of course, someone was playing to an audience. The debate hinged on a deeper tension in SETI. Are we searching for signals designed to be found, or are we hoping to stumble across something never meant for us? The Drake equation signal blurred that line. If it was deliberate, it implied a sender not just aware of our existence but familiar with our scientific frameworks. That raised unsettling possibilities. Had another civilization studied us from afar, crafting a signal tailored to our expectations? Or was this a cosmic prank, a quirk of nature mimicking intelligence? As researchers dug deeper, the mystery only deepened. The signal's point of origin was traced to a region near the constellation Ophiuchus, but no obvious star system stood out as a likely host. There were no repeating patterns, no secondary confirmations, just this one tantalizing blip. Without repetition, the signal faded into ambiguity, leaving behind more questions than answers. What makes this case fascinating isn't just the signal itself, but what it reveals about our search strategies. The Drake equation isn't just a tool for estimating alien civilizations, it's a reflection of our biases. We look for what we think aliens might send based on how we would communicate. The 2003 signal held up a mirror to that assumption, forcing us to ask, are we too focused on finding versions of ourselves in the cosmos? This isn't just academic navel-gazing. Future telescopes like the Square Kilometre Array will scan millions of frequencies simultaneously, vastly expanding our search beyond the water hole. But the Drake equation signal reminds us that the real challenge might not be technical, it's imaginative. If another civilization is out there, their perfect signal might not look anything like ours. So where does that leave us? The signal remains unexplained, a fleeting whisper that almost fit the mold. Whether it was a cosmic coincidence or a deliberate nod, it underscores a humbling truth: the universe owes us nothing. It won't conform to our equations or our hopes, but that's what makes the search so thrilling. Every dead end teaches us something new, and every near miss keeps the flame of curiosity burning. And speaking of curiosity, our next signal takes us to the edge of the unknown, a cluster of enigmatic emissions from the heart of Orion's belt that defied explanation for decades. Now, shifting our gaze to a cosmic landmark that's captivated humanity for millennia, Orion's belt, we encounter a puzzle that began unfolding in the 1980s. Amid the familiar trio of stars, astronomers detected a series of bizarre signals, clustered in a way that defied natural explanation. Unlike the isolated blips we've seen with other cosmic mysteries, these emissions seem to whisper from the same patch of sky, sparking debates that still linger today. Were they the birth cries of distant planetary systems, or something far more intentional? The signals emerged during a routine survey of the Orion Molecular Cloud Complex, a sprawling stellar nursery where stars and planets are born. At first, researchers assumed they'd stumbled upon the radio chatter of protoplanetary disks, massive rings of gas and dust swirling around infant stars. These disks often emit erratic signals as particles collide and magnetic fields twist, but the Orion signals had quirks that didn't quite fit. Their patterns weren't chaotic, they pulsed with faint regularity like a heartbeat. Stranger still, they clustered around a region devoid of obvious young stars, a cosmic quiet zone where such activity seemed unlikely. This anomaly led some scientists to propose a radical idea. Could these signals be evidence of directed panspermia, the deliberate seeding of life across the cosmos? The theory, first floated by Nobel laureate Francis Crick and chemist Leslie Orgel, suggests that advanced civilizations might distribute microbial life to habitable worlds. Orion, with its dense molecular clouds, would be an ideal delivery zone for such an effort. The signals in this scenario might not be messages at all, but markers, cosmic breadcrumbs left by a long-gone culture pointing toward fertile planetary systems. Of course, skepticism abounds. Critics argue that attributing unexplained signals to alien activity is a classic God of the gaps fallacy, filling knowledge voids with speculation. They point to more mundane explanations, like interference from human satellites or glitches in early radio telescopes. But the timing is curious. The signals vanished by the 90s, just as our observational tools improved. Was this a case of technology outpacing the phenomenon, or did the sender simply stop transmitting? What keeps the Orion mystery alive is its tantalizing context. Orion's belt is more than a navigational landmark. It's woven into human mythologies as a gateway or a meeting place of gods. That cultural weight makes the signals feel like a cosmic wink, as if the universe is playing with our penchant for pattern seeking. Scientifically, though, the lesson is pragmatic. Sometimes the most intriguing signals emerge from the gaps between our understanding and our imagination. As we turn next to the Aquarius riddle, another signal that played with mathematical precision, remember, the cosmos rarely follows our scripts. Whether natural or engineered, these whispers remind us that the universe's greatest mysteries often lie just beyond the edge of our theories. Now, as we drift from the mythic trails of Orion into the cosmic waters of Aquarius, we encounter a signal so precise it seemed to hum with the rhythm of mathematics itself. The Aquarius riddle began in the 1970s when astronomers picking up faint radio waves noticed something extraordinary. The pulses weren't random. They repeated at intervals so regular they could be plotted like clockwork, sparking debates that split scientific opinion down the middle. Was this the natural thrum of a distant stellar object, or a deliberate signal etched into the fabric of space? The source of these pulses, catalogued as Aquarius A, emitted bursts every 107.3 seconds, a cadence so exact it defied the erratic behavior typical of cosmic phenomena. At first, researchers suspected a neutron star, a collapsed stellar core known to spin with metronomic precision. But neutron stars usually slow down over time as they lose energy, their pulses growing fainter and less frequent. Aquarius A, however, held its tempo for years without variation, as if governed by an unshakable cosmic metronome. This peculiar stability led some to propose an even stranger explanation: harmonics. Just as a plucked guitar string vibrates at specific frequencies, the intense magnetic fields around neutron stars can theoretically resonate in predictable patterns. If Aquarius A's pulses were harmonics, they'd offer a rare glimpse into the physics of extreme stellar environments, a natural explanation wrapped in layers of celestial complexity. Yet not everyone was satisfied. The signal's location added fuel to the speculative fire. Aquarius originated near the edge of our galaxy, in a region sparse with stars, a quiet backwater where such a precise natural emitter seemed oddly out of place. This isolation fueled alternative theories, the most provocative being the alien beacon hypothesis. If an advanced civilization wanted to broadcast its presence, proponents argued, what better way than a signal that repeats with mathematical clarity? Unlike the chaotic noise of the cosmos, a timed pulse would stand out like a lighthouse in a storm. Even the frequency matched predictions for a deliberate beacon, a narrowband emission easy to distinguish from background static. The idea wasn't entirely fringe. Renowned astronomer Nikolai Kardashev had theorized that advanced societies might use such signals to announce themselves across interstellar distances. Skeptics, of course, countered with Occam's razor. Why invoke aliens when neutron stars, however odd their behavior, were proven to exist? They pointed to FRB 1957+20, a pulsar nicknamed the Black Widow for its bizarrely stable spin, as evidence that nature could produce rhythmic signals without extraterrestrial help. Others suggested interference from early human satellites, though none matched Aquarius A's timing or frequency. The riddle deepened when the signal abruptly ceased in the 1980s, leaving behind no traces, just questions. What makes the Aquarius riddle endure isn't just the mystery of its origin, but what it reveals about our approach to cosmic anomalies. When faced with the unknown, science walks a tightrope between imagination and evidence. The signal's mathematical beauty tugs at our instinct to find intention in the universe, while its unresolved fate reminds us that some puzzles are content to linger in the shadows. As we pivot next to the interstellar visitor known as Oumuamua, keep this in mind: sometimes the most ordinary explanations are the hardest to prove, and the wildest ones are the hardest to dismiss. The cosmos, it seems, enjoys keeping us guessing. Now, shifting our gaze from the enigmatic pulses of Aquarius to an object that streaked through our solar system like a cosmic messenger, we arrive at the mysteries surrounding Oumuamua. This interstellar visitor, first detected in 2017, wasn't just unusual, it defied nearly every expectation scientists had for an asteroid or comet. Its elongated shape, its unexpected acceleration as it moved away from the sun, and whispers of faint radio signals all sparked a debate that continues to reverberate through astronomy. Was Oumuamua a natural oddity sculpted by the forces of deep space, or something far more extraordinary? When telescopes first caught sight of Oumuamua, its proportions alone were startling. Unlike the lumpy, potato-like asteroids common in our solar system, this object was at least 10 times longer than it was wide, a shape resembling a cigar or perhaps a pancake. No one had ever seen anything like it. Then came the real puzzle: its trajectory. As it slingshotted past the sun, rather than slowing down as expected, it sped up slightly. Comets often exhibit similar behavior as their icy surfaces vaporize, creating a natural propulsive force. But Oumuamua showed no visible coma, no telltale tale of gas and dust. This left astronomers scrambling for explanations. One theory pointed to solar heating. As Oumuamua neared the sun, hidden reservoirs of hydrogen ice beneath its surface might have warmed and sublimated, releasing gas just enough to nudge it forward without visible outgassing. Hydrogen, being nearly invisible to telescopes, could explain the lack of a trail. Another idea suggested it was a shard of a Pluto-like world, ripped away by some ancient collision, with nitrogen ice that vaporized silently in the sun's heat. Both hypotheses leaned on known physics, yet neither could fully account for the object's bizarre acceleration or its peculiar shape. Enter Avi Loeb, the Harvard astrophysicist who dared to voice a provocative alternative. What if Oumuamua wasn't natural at all? Loeb argued that its acceleration, paired with its unusual geometry, matched what we'd expect from a light sail, a hypothetical spacecraft propelled by solar radiation. Such technology, though beyond our current capabilities, is theoretically plausible for an advanced civilization. The lack of visible outgassing in this view wasn't a missing clue but evidence of artificial design. Even the faint radio emissions some claim to detect, though later dismissed as noise, were seized upon as potential signs of debris or dormant machinery. Critics, of course, bristled at the extraterrestrial hypothesis. They pointed out that extraordinary claims require extraordinary evidence, and Oumuamua's oddities, while unexplained, didn't definitively point to alien engineering. The interstellar visitor could simply be a fragment of an exoplanet's crust, shaped by forces we've yet to observe elsewhere. Others noted that its trajectory, while unusual, wasn't impossible for a comet depleted of surface volatiles. The scientific community remains divided, with many urging caution against leaping to interstellar conclusions. What makes Oumuamua so compelling isn't just the unresolved debate, but what it reveals about our hunger for cosmic company. Its fleeting passage forced us to confront the limits of our knowledge and the tantalizing possibility that the universe might be stranger and more populated than we've dared to imagine. As we turn next to the eerie signals emerging from the depths of dark flow, remember this: sometimes the most profound mysteries aren't just about what we find, but what we're forced to reconsider along the way. Now, venturing beyond the curious case of Oumuamua, we plunge into one of cosmology's most perplexing enigmas, the eerie phenomenon known as dark flow. Imagine the universe as a vast ocean with galaxies drifting like ships on its surface. But what if something unseen, something colossal, was tugging them all in the same direction? That's the essence of dark flow, a controversial pattern in the cosmic microwave background that suggests entire clusters of galaxies are moving toward a mysterious, invisible force beyond the edge of our observable universe. The story begins with the cosmic microwave background, or CMB, the faint afterglow of the Big Bang that permeates all of space. In 2008, astronomers studying this ancient light noticed something bizarre. Galaxy clusters weren't just drifting randomly, they appeared to share a common motion, streaming toward a single point in the sky near the constellations Centaurus and Vela at speeds exceeding 2 million miles per hour. This wasn't just a slight statistical quirk, it defied the standard model of cosmology, which assumes the universe's expansion should distribute matter evenly with no preferred direction. One theory to explain this motion invokes the gravitational pull of something unimaginably vast, a structure so enormous it lies beyond our cosmic horizon. Perhaps it's a supercluster of galaxies or even another universe, exerting its influence through a hidden dimension or a cosmic filament we can't yet detect. This idea dovetails with multiverse hypotheses, where our universe is just one bubble in an infinite foam of others, each with its own physical laws. If a neighboring universe brushed against ours in the distant past, the gravitational aftershocks could still be nudging galaxies today. Critics, however, argue that dark flow might be an illusion, an artifact of incomplete data or biases in how we measure the CMB. Some suggest that our local galaxy cluster, the Laniakea supercluster, could be warping observations, creating the false impression of a larger flow. Others point to the Planck satellite's later measurements, which failed to confirm the original findings. Yet the debate isn't settled. The Planck data had its own limitations, and newer studies hint that dark flow might persist on even larger scales beyond what current telescopes can resolve. What makes dark flow so tantalizing isn't just the science, it's the philosophical implications. If confirmed, it would mean our universe isn't as self-contained as we thought. There could be realms beyond our sight, their gravity reaching across the void to guide the motion of galaxies like invisible hands. Or perhaps it's a reminder that even our most precise instruments are still grappling with the universe's complexities. Either way, dark flow challenges us to rethink the very fabric of reality. As we turn next to the strange bursts echoing from the heart of our galaxy, keep this in mind sometimes. The most profound discoveries aren't just about what we observe, but about the boundaries they force us to question. The universe, it seems, still holds cards close to its chest. Now, shifting our gaze from the mysterious pull of dark flow, let's zoom into the chaotic heart of our own galaxy, where Sagittarius, a star, the supermassive black hole at the center of the Milky Way, has been sending out bizarre radio bursts that defy easy explanation. These aren't your typical cosmic static, they're erratic, unpredictable, and packed with enough energy to light up entire star systems. What's causing them? The answer might lie in the violent dance of matter around a black hole, or something even more extraordinary. Picture this. Every few hundred or thousand years, a star or gas cloud strays too close to Sagittarius, a star's event horizon, the point of no return. As it's torn apart by tidal forces, the debris forms a swirling disk of superheated plasma, screaming with radio waves as it spirals into oblivion. These tidal disruption events could explain some of the bursts we've detected, especially the ones that flare up suddenly and then fade. But here's the twist, not all the signals fit this pattern. Some repeat at irregular intervals, flickering like a malfunctioning beacon, while others carry odd spectral features, hints of structure that don't quite match known astrophysical processes. That's where the speculative fun begins. Could these anomalies be signs of something artificial? A handful of researchers, like those at the Breakthrough Listen project, have floated the idea that advanced civilizations might use the galactic center as a natural relay station. Think of it as a cosmic Times Square, a place where signals could be amplified by the black hole's gravity and broadcast across the galaxy. One particularly puzzling burst detected in 2019 even had a rhythmic quality, almost like a coded pulse. Of course, the more likely explanation involves magnetars, super-dense, highly magnetized neutron stars, or shock waves from colliding gas clouds. But the sheer strangeness of some bursts keeps the door open to wilder possibilities. Critics, though, urge caution. The galactic center is a crowded, turbulent place packed with neutron stars, rogue planets, and swirling magnetic fields. Isolating a single signal's origin is like trying to hear a whisper in a hurricane. Even the rhythmic burst could be explained by quasi-periodic oscillations, a phenomenon where clumps of matter in the accretion disk orbit at set intervals, creating predictable flickers. And let's not forget, Sagittarius, a star, is relatively quiet compared to other supermassive black holes. If aliens were using it as a hub, why aren't the signals clearer? Yet the mystery persists because of what these bursts represent, a frontier. The center of our galaxy is both a laboratory for extreme physics and a blank spot on the map where imagination races ahead of data. Future telescopes, like the Square Kilometre Array, could untangle the signal's origins by mapping their polarization or pinpointing exact locations. Until then, the bursts from Sagittarius A star remind us that even in our cosmic backyard, there are whispers we don't yet understand. As we prepare to delve into the next enigma, unexplained echoes from the Perseus cluster, consider this: sometimes the most profound questions aren't just about what's out there, but about how little we truly know of the forces shaping our galaxy from within. Now, let's journey from the chaotic core of our galaxy to the vast expanse of the Perseus cluster, a gathering of thousands of galaxies over 200 million light-years away. Here, astronomers have detected eerie echoes, subtle, repeating signals that seem to ripple through the cosmos like whispers in a cathedral. Unlike the violent bursts from Sagittarius A star, these are faint, almost ghostly, as if the universe itself is humming a tune we can barely hear. At first glance, the Perseus cluster seems like an unlikely place for mysteries. It's one of the most massive objects in the known universe, a titanic web of galaxies bound together by gravity. Yet, in 2016, researchers analyzing data from the Chandra X-ray Observatory stumbled upon something odd: rhythmic X-ray pulses emanating from the cluster's heart. The signals weren't random. They followed a pattern, repeating every few hours with eerie precision. What could possibly produce such a steady cosmic drumbeat in a place where chaos should reign? One leading theory points to dark matter, the invisible glue holding galaxies together. Some physicists speculate that certain types of dark matter particles, like actions, could interact weakly with magnetic fields, emitting faint X-rays as they decay or collide. If true, these echoes might be our first direct glimpse into the shadowy realm that makes up 85% of the universe's matter. Imagine, the hum of the Perseus cluster could be the death rattle of particles we've hunted for decades, finally revealing themselves in the depths of space. But there's another, even more dramatic possibility: primordial black holes. These aren't the black holes formed from collapsing stars. Instead, they're thought to be relics of the Big Bang itself, tiny yet incredibly dense, peppered throughout the cosmos like cosmic shrapnel. If two of these ancient objects were to merge within the Perseus cluster, the resulting shock waves could send tremors through the hot gas between galaxies, producing the rhythmic X-rays we've observed. It's a tantalizing idea, suggesting that some of the universe's oldest inhabitants might still be lurking in the darkness, leaving traces of their collisions. Skeptics, of course, have alternative explanations. The pulses could stem from something far more mundane, like the sloshing of superheated gas in the cluster's core. As galaxies move through the cluster, they stir the surrounding plasma, creating pressure waves that might mimic the observed signals. Others suggest the echoes could be artifacts of the instruments themselves, quirks in how X-ray detectors process faint emissions from such distant sources. Yet the allure of the Perseus echoes lies in their persistence. Unlike one-off anomalies, these signals have been detected multiple times, their rhythm unwavering across years of observations. That consistency makes them harder to dismiss as mere noise. Future telescopes, like the European Space Agency's Athena mission, could settle the debate by mapping the cluster's X-rays in unprecedented detail, potentially pinpointing the source of these cosmic vibrations. What's at stake goes beyond a single cluster. If the echoes are tied to dark matter or primordial black holes, they could reshape our understanding of the universe's structure, evolution, and even its ultimate fate. The Perseus cluster isn't just a distant curiosity, it's a testing ground for some of the boldest ideas in modern physics. As we turn our attention to the next mystery, the enigmatic silence of the Boots void, remember this. The universe speaks in many voices. Some shout like the bursts from Sagittarius A star, others murmur like the echoes of Perseus, and sometimes the most profound revelations come not from the noise but from the quietest whispers in the dark. Now let's venture into one of the most hauntingly empty places in the cosmos, the Boots void, a region of space so vast and barren that astronomers call it the Great Nothing. Stretching over 300 million light-years across, this cosmic desert contains fewer galaxies than you could count on one hand, a stark contrast to the bustling clusters we've explored so far. Yet, in this near-empty expanse, a solitary signal was detected, one that defies everything we know about how the universe should behave. The Boots void isn't just empty by chance. It's a supervoid, a relic of the universe's infancy, where matter somehow failed to clump together during the Big Bang's aftermath. Most supervoids are quiet, their emptiness making them unremarkable until 2015, when researchers picked up an anomalous radio emission from its heart. The signal was faint but unmistakable, a narrowband transmission that stood out against the silence like a single candle in a darkened room. What made it so intriguing wasn't just its presence, but where it came from. In a void, there's almost nothing to generate such a signal naturally. No star-forming regions, no active galactic nuclei, just emptiness. This raises a spine-tingling question. Could the signal have been meant to be found? Some scientists argue that the void's isolation makes it an ideal target for hypothetical extraterrestrial civilizations. If you wanted to send a beacon that wouldn't drown in cosmic noise, a supervoid would be the perfect place. The signal's narrowband nature, typical of artificial transmissions, only fuels this speculation. Unlike the chaotic bursts of FRBs or the hum of dark matter, this emission was precise, almost engineered. Researchers even compared it to humanity's own deliberate broadcasts like the Arecibo Message, and found unsettling similarities in its structure. But before we jump to conclusions, let's consider the natural explanations. One possibility involves rogue galaxies, lonely, star-rich islands drifting through the void. Though rare, these galaxies could host unusual stellar phenomena like hyperactive magnetars or colliding neutron stars capable of producing such a signal. Another theory points to gravitational lensing, where the void's sheer emptiness acts as a cosmic magnifying glass, bending and amplifying distant background emissions into what appears to be a localized transmission. It's a clever trick of physics, but one that doesn't fully explain the signal's peculiar characteristics. Then there's the timing. The signal appeared only once, never repeating despite years of follow-up observations. This fleeting nature makes it eerily similar to the WOW signal, another one-off transmission that vanished into legend. Was it a fluke, a glitch in the data, or something far more deliberate, a cosmic ping sent across the void to test whether anyone was listening? The Boots void transmission forces us to confront a deeper paradox. In a universe teeming with noise, silence can be just as unnerving. If the signal was artificial, its sender would need to understand something profound about the void's rarity and our curiosity. After all, what better way to ensure a signal stands out than by planting it in the last place we'd expect to find one? As we prepare to unravel the next mystery, the disputed signals from Kepler 438b, remember this: the universe's greatest enigmas aren't always hidden in the chaos. Sometimes they're waiting in the quietest corners, where the absence of everything makes the presence of anything impossible to ignore. Now, let's turn our attention from the eerie silence of the Boots void to a world that might just be a cosmic neighbor. Kepler 438b, an exoplanet that's been called one of the most Earth-like worlds ever discovered. Orbiting a red dwarf star about 640 light-years away, this distant planet sits snugly in its star's habitable zone, where temperatures could allow liquid water to exist. But what truly caught astronomers' attention wasn't just its potential for life. It was a bizarre, disputed signal that seemed to emanate from its direction, sparking debates that still linger today. The signal in question was detected in 2015, shortly after Kepler 438b's discovery. It wasn't a dramatic burst or a repeating pattern, but a faint, narrowband radio emission, the kind often associated with artificial sources. For a fleeting moment, scientists dared to wonder, could this be a technosignature, a deliberate transmission from an advanced civilization? The idea wasn't entirely far-fetched. After all, if life had arisen on this Earth-like world, might it have also developed the means to reach out across the stars? But before we entertain visions of alien cities, let's ground ourselves in the science. Red dwarf stars, like the one hosting Kepler 438b, are notorious for their violent flares. These eruptions can unleash torrents of radiation, capable of distorting radio signals and creating false positives. Some researchers argue that the anomaly could simply be the result of stellar activity, a cosmic mirage conjured by the star's temper. In fact, follow-up observations failed to detect the signal again, casting doubt on its extraterrestrial origins. Yet the mystery deepens when we consider the planet's harsh reality. Kepler 438b is likely tidally locked, with one side forever facing its star and the other shrouded in eternal night. Red dwarfs also bombard their planets with intense ultraviolet radiation, which could strip away atmospheres over time. If life does exist there, it would need to be extraordinarily resilient, perhaps huddling in underground oceans or beneath thick layers of ice. Could such a civilization develop advanced technology, let alone the means to broadcast signals into space? It's a tantalizing but daunting question. Then there's the matter of distance. At 640 light-years away, any signal from Kepler 438b would have left its source long before human civilizations even existed. If it was artificial, the senders might be long gone, their message drifting through the void as a ghostly echo of a once thriving world. This sobering thought raises another possibility. What if we're detecting the last gasp of a dying civilization, a final attempt to be remembered in a universe that forgets so easily? Of course, not everyone is convinced. Skeptics point to humanity's own radio leakage satellites, military radar, and other terrestrial interference as a more likely culprit. The signal's frequency overlapped with bands used by human technology, making contamination a real concern. Even the most optimistic SETI scientists admit that extraordinary claims require extraordinary evidence, and so far, the Kepler 438b anomaly hasn't provided it. But here's what makes this signal so fascinating. It lives in the gray area between hope and skepticism, a reminder that the search for extraterrestrial intelligence is as much about patience as it is about discovery. Every ambiguous signal forces us to refine our methods, to separate cosmic whispers from wishful thinking. Kepler 438b may not have given us proof of aliens, but it has given us something equally valuable, a lesson in humility. The universe is vast, and its secrets are rarely handed to us on a silver platter. As we move forward, keep this in mind. The next great discovery might not come with fanfare or flashing lights. It could arrive as a whisper, a fleeting anomaly that challenges everything we thought we knew. And when it does, we'll be ready to listen. Now, let's journey deeper into the cosmos, where another enigma awaits: the erratic signals of Cygnus X3, a binary system that defies explanation with its unpredictable behavior. What strange forces are at play in this celestial dance? The answers might just rewrite the rules of astrophysics. Now, shifting our gaze to a celestial oddity that has baffled astronomers for decades, we arrive at Cygnus X3, a binary system that refuses to play by the rules. Nestled in the constellation Cygnus, this cosmic duo consists of a compact object, likely a neutron star or black hole, locked in a gravitational tango with a massive companion star. What makes Cygnus X3 so extraordinary isn't just its composition, but the bizarre, unpredictable signals it emits, flickering like a cosmic strobe light with no discernible rhythm. At first glance, Cygnus X3 fits the profile of a microquasar, a miniature version of the supermassive black holes that power quasars. In this model, the compact object sucks material from its companion, forming a superheated accretion disk that jets particles at near light speed. These jets, when pointed toward Earth, should produce regular X-ray and radio flares, but Cygnus X3 doesn't obey expectations. Its emissions erupt in chaotic bursts, sometimes vanishing for years before reappearing without warning. This erratic behavior has led some scientists to propose that we're witnessing something far stranger, perhaps even evidence of ancient alien engineering. Let's unpack the microquasar theory first. When matter spirals into a compact object, it doesn't go quietly. Friction heats the gas to millions of degrees, generating X-rays. Occasionally, magnetic fields funnel some of this material into jets, which can outshine the entire system. For most microquasars, these processes follow rough timetables. But Cygnus X3's jets seem to switch on and off at random, defying conventional physics. Some researchers suggest the companion star's stellar winds might be to blame, smothering the jets like a cosmic blanket. Others speculate that the compact object's spin is wobbling unpredictably, like a top losing balance. Yet there's a more provocative idea lurking in the shadows. A fringe group of theorists proposes that Cygnus X3's oddities could point to artificial origins. Imagine for a moment an ancient megastructure, a Dyson sphere or a particle accelerator built by a long-vanished civilization orbiting the compact object. Such a construct might harvest energy from the accretion disk, occasionally leaking radiation in patterns we mistake for natural flares. It's a radical notion, but not without precedent. In the 1970s, radio bursts from Cygnus X3 seemed to arrive at intervals matching pi, the mathematical constant. Coincidence, perhaps? But the idea that an advanced culture might encode messages in fundamental numbers is a trope straight out of science fiction. Before we get carried away, let's ground this in reality. The pi-like signal was later debunked as a statistical fluke, and no repeat patterns have been confirmed since. Mainstream astrophysics still favors natural explanations, however incomplete they may be. One compelling theory involves precessing jets. Imagine a garden hose whipping around, its stream slicing through the air in erratic arcs. If Cygnus X3's jets are wobbling due to gravitational disturbances, their intermittent visibility from Earth could explain the irregular flares. But here's where the plot thickens. In 2008, astronomers detected ultra-high-energy gamma rays from Cygnus X3, a phenomenon typically associated with supermassive black holes, not stellar-sized ones. How could a microquasar produce such monstrous energy? Some models suggest the companion star's wind collides with the jets, creating shock waves that accelerate particles to extreme speeds. Others whisper about unknown physics or something even more exotic. What makes Cygnus X3 so compelling is its refusal to fit neatly into any box. It's a cosmic rogue challenging our understanding of how compact objects behave. Whether it's a natural oddity or something more speculative, one thing is clear: this binary system holds secrets that could reshape astrophysics. And as we continue to monitor its capricious signals, we're reminded that the universe's greatest mysteries often lie in the details we can't yet explain. Now let's turn our attention to another cosmic puzzle, the Geminga Enigma. This nearby pulsar shouldn't be so quiet, yet its radio silence speaks volumes. What hidden mechanisms are at work in this stellar remnant? The answers might just redefine what we know about neutron stars. Now, let's venture into the quiet yet puzzling world of Geminga, a neutron star that's anything but ordinary. Just 500 light-years away, this celestial neighbor should be a radio chatterbox like most pulsars. Instead, it's nearly mute in radio waves but blazes with gamma rays, a contradiction that's left scientists scratching their heads. What makes Geminga so unusual, and why does it break the rules we've come to expect from neutron stars? Discovered in the 1970s by its gamma-ray emissions, Geminga was a mystery from the start. Unlike typical pulsars, which announce themselves with rhythmic radio pulses, Geminga stayed silent in radio frequencies for years. It wasn't until the 1990s that faint X-ray and gamma-ray pulses were detected, revealing its true nature as a spinning neutron star. But even then, its radio silence was baffling. Most pulsars act like cosmic lighthouses, beaming radio waves from their magnetic poles as they rotate. Geminga, though, seems to have misplaced its radio beam or chosen not to use it. So, why the silence? One leading theory points to Geminga's unique orientation. Imagine a lighthouse where the light beam points almost directly away from Earth. You'd barely see a flicker, if anything at all. That might be the case here. Geminga's radio beam could simply be missing us, while its gamma rays emitted in a wider cone still reach our telescopes. But there's a twist. Even when accounting for this geometry, Geminga's radio emissions are far weaker than expected. Some researchers suggest its magnetic field is structured differently, perhaps with a death valley where radio production shuts down. Then there's the gamma-ray puzzle. Geminga is one of the brightest gamma-ray sources in the sky, yet its energy output doesn't neatly fit standard pulsar models. Normally, gamma rays are thought to arise from particles accelerated near the neutron star's magnetic poles or in its swirling magnetosphere. But Geminga's gamma-ray pulses are oddly smooth, lacking the sharp peaks seen in other pulsars. This has led to alternative ideas, like gamma rays being produced farther out, in a halo of energetic particles surrounding the star. But the intrigue doesn't stop there. Geminga is also racing through space at breakneck speed, leaving a faint tail of particles in its wake like a cosmic comet. This wake hints at a violent past, possibly a supernova kick that sent the neutron star hurtling outward. Yet, despite its speed, Geminga shows no trace of a radio pulsar wind nebula, a cloud of particles typically seen around fast-moving pulsars. Where did it go? One possibility is that Geminga's magnetic field is too weak to generate the usual shock waves, rendering its nebula invisible to our instruments. The most tantalizing question, though, is whether Geminga represents a whole class of hidden neutron stars. Astronomers estimate there could be tens of millions of neutron stars in our galaxy, but we've only found a fraction of them. Could many be like Geminga, quiet in radio but glowing in gamma rays, lurking unnoticed in plain sight? If so, current surveys might be missing a silent majority of these stellar remnants, dramatically undercounting their true numbers. As we piece together Geminga's secrets, we're reminded that neutron stars are far more diverse than we once thought. From its missing radio pulses to its enigmatic gamma rays, this cosmic oddity challenges textbook assumptions, pushing us to rethink how these dense stellar corpses behave. And with every new observation, Geminga whispers a tantalizing possibility that the universe's most ordinary-looking objects might hold the most extraordinary surprises. Next, we'll turn our gaze to another cosmic riddle Hoag's object, a galaxy that defies classification. Its perfect ring of stars raises questions about formation, stability, and whether we're seeing the handiwork of an unseen force. Now, shifting our cosmic lens, we arrive at one of the most visually stunning enigmas in the night sky, Hoag's object. This rare ring galaxy, floating some 600 million light-years away, is a celestial donut, a perfect circle of young, blue stars surrounding an ancient yellow core with an almost empty gap in between. But beyond its beauty, Hoag's object has puzzled astronomers with strange radio and infrared emissions that don't quite match typical galactic behavior. What's causing these odd signals, and could they hint at something extraordinary happening within this cosmic oddity? Discovered in 1950 by astronomer Arthur Hoag, this galaxy defies easy classification. Most ring galaxies form through violent collisions where a smaller galaxy punches through a larger one, triggering star formation in a ripple-like ring. But Hoag's object shows no signs of such a collision, no debris, no distortion in its core, no neighboring galaxy that could have caused the disruption. It's as if the ring appeared out of nowhere, a stellar halo frozen in time. The mystery deepens when we examine its emissions. Unlike most galaxies, which radiate predictable patterns of radio waves tied to star formation or supermassive black holes, Hoag's object emits sporadic, localized bursts. Some of these signals cluster along the ring itself, suggesting intense but isolated pockets of activity, perhaps regions where stars are forming under unusual conditions. Others flicker from the gap between the core and the ring, a space that should be nearly devoid of material. One theory proposes that hidden streams of gas, too faint to detect directly, might be funneling into these gaps, igniting brief but powerful bursts of energy. Then there's the infrared puzzle. The ring glows unusually bright in infrared light, far more than its visible starlight would predict. This excess implies vast amounts of dust heated by young stars or other energetic processes. But where did this dust come from? Normally, galaxies this old, its core is estimated at over 10 billion years, should have exhausted or expelled most of their dust long ago. Some scientists speculate that the ring might be recycling material, with dying stars seeding new generations in a self-sustaining cycle. Others wonder if the galaxy cannibalized a gas-rich neighbor, though no evidence of such a feast remains. The most tantalizing idea, though, is that Hoag's object might not be alone in its oddity. A handful of similar ring galaxies, dubbed Hoag-type objects, have been found in recent years, each with their own quirks. Could these galaxies represent a rare but natural phase of galactic evolution, one where internal dynamics rather than collisions sculpt their rings? Computer simulations suggest that under precise conditions, gravitational instabilities in a galaxy's disk might naturally form stable rings over billions of years. If true, Hoag's object could be a cosmic clock capturing a fleeting moment in a galaxy's life cycle. Of course, no discussion of unexplained signals would be complete without at least glancing toward the fringe. The ring's near-perfect symmetry and its anomalous emissions have led some to propose, however speculatively, that such structures could be signatures of advanced civilizations. Imagine a Dyson swarm, a megastructure built to harness a star's energy, arranged in a deliberate ring, or consider directed energy broadcasts purposefully designed to stand out against the galactic background. While these ideas stretch conventional astronomy, they underscore how Hoag's object challenges our assumptions about what's natural in the cosmos. What makes Hoag's object so compelling isn't just the unanswered questions, it's the reminder that galaxies, like snowflakes, might follow broad patterns but never repeat exactly. Whether its signals stem from exotic physics, overlooked processes, or something even more extraordinary, this cosmic ring urges us to keep looking deeper. Because sometimes the universe's most profound lessons hide in plain sight, wrapped in a circle of starlight. Up next, we confront the eerie quiet of the cosmos with our final signal, the Great Silence Paradox, where the absence of expected messages forces us to rethink our place in the universe. Now, as we approach the end of our cosmic journey, we're left staring into a silence so profound it speaks volumes, the Great Silence Paradox. This isn't just about the signals we've detected, but the ones we haven't. If the universe is teeming with potential for life, as its vastness suggests, why does it feel so overwhelmingly quiet out there? This question lies at the heart of Fermi's famous paradox, named after physicist Enrico Fermi, who first posed it bluntly: where is everybody? Let's break down the puzzle. Our galaxy alone contains hundreds of billions of stars, many with planets in habitable zones. Even if only a tiny fraction of these developed intelligent life, the cosmos should be buzzing with signals, artifacts, or signs of activity. Yet, despite decades of searching, from radio telescopes scanning the skies to probes scouring our solar system for alien relics, we've found nothing conclusive. The silence is deafening. One explanation is the rare Earth hypothesis. It argues that while simple life might be common, the conditions needed for complex, intelligent life are extraordinarily rare. Earth's perfect storm, a stable star, a protective moon, plate tectonics, even Jupiter-deflecting asteroids, might be a cosmic fluke. If true, the silence isn't surprising. We might truly be alone, or at least lonely in a sea of microbial life. But another camp proposes darker answers. Maybe civilizations inevitably hit a self-destructive wall, nuclear war, runaway AI, ecological collapse before they can broadcast their presence. This great filter theory suggests that something, whether natural or self-inflicted, wipes out advanced societies. If so, the silence could be a warning sign, a cosmic graveyard of civilizations that didn't make it past their technological adolescence. Then there are the more optimistic, if speculative, ideas. Perhaps advanced civilizations exist but have moved beyond noisy radio signals, communicating through undetectable means like quantum entanglement or neutrino beams. Or they might choose to stay hidden, observing us like a cosmic wildlife preserve, the zoo hypothesis. Some even suggest that aliens could be among us already, camouflaged as mundane phenomena or operating in dimensions we can't perceive. The Great Silence forces us to confront uncomfortable truths. It could mean we're special, doomed, or simply ignorant, but it also highlights how young we are in cosmic terms. Human radio signals have barely traveled 100 light years. We've been listening for alien whispers for less than a century. The universe is 13.8 billion years old. We might just be late to the conversation or too early to hear the next one. As we close this exploration of galactic mysteries, remember, silence isn't empty. It's a canvas for our curiosity. Every unexplained signal, every quiet corner of space invites us to question, imagine, and search harder. Because in the end, the universe's greatest mystery might not be the signals we detect, but what its silence is trying to tell us. If these cosmic enigmas sparked your imagination, don't let the conversation end here. Hit like, subscribe, and tap that notification bell to join us for more deep dives into the universe's unsolved puzzles. And in the comments, tell us what's your take on the Great Silence. Are we alone, unlucky, or just not listening the right way? The cosmos is waiting for your theories. And so, as we reach the final stretch of our journey through the cosmos, let's take a moment to reflect on the extraordinary tapestry of signals we've uncovered. From the tantalizing blip of the WOW signal to the rhythmic pulses of FRB 180,916, each mystery has challenged our understanding of the universe and ourselves. These aren't just random anomalies, they're cosmic breadcrumbs pointing us toward questions we're only beginning to formulate. Consider the sheer diversity of these enigmas. The repeating fast radio bursts defying known physics, the controversial alien signals like SETI 02 plus 14a that teeter between interference and intention, and the haunting silence of the Great Paradox, all of them push science to its limits. They force us to revisit old assumptions, whether it's dismissing the LGM-1 pulsar as extraterrestrial chatter, or debating whether Tabby stars are dimming is a swarm of comets or something far more extraordinary. What ties these mysteries together isn't just their strangeness, but what they reveal about our place in the cosmos. The Lorimer burst's staggering energy hints at cosmic events we can't yet imagine, while signals like BLC-1 remind us of the delicate line between human noise and potential contact. Even the false alarms, the Andromeda signal, the Vulcan wave teach us something invaluable, the importance of skepticism married to relentless curiosity. Theories abound, from the grounded to the fantastical. Magnetars, evaporating black holes, and neutron star wobbles offer plausible explanations for some signals, while others, like the mathematical precision of the Aquarius riddle or Oumuamua's disputed emissions, keep the door open to wilder possibilities. And let's not forget the cultural impact. The WOW signal inspired generations of scientists, while the Arecibo response blurred the lines between hoax and hope. But here's the beautiful truth. These mysteries aren't failures of science, they're invitations. Every unsolved signal is a reminder that the universe is vaster, weirder, and more wonderful than we've dared to dream. They challenge us to build better telescopes, refine our theories, and stay open to the idea that the next great discovery might be lurking in the static of a radio wave or the flicker of a distant star. So as we wrap up this cosmic tour, I'll leave you with a question not just about aliens or black holes, but about you. Which of these 30 signals captured your imagination the most? Was it the eerie repetition of FRB 121,102, the enigmatic Ross 128 anomaly, or the spine-tingling possibilities of the Great Silence? Drop your thoughts in the comments below. Let's keep this conversation as boundless as the universe itself. And if these galactic puzzles left you hungry for more, don't forget to hit subscribe and ring that notification bell. Because the cosmos isn't done surprising us, not by a long shot. From vanishing stars to dark matter's secrets, there are countless mysteries waiting for their moment in the spotlight. Stay curious, stay questioning, and above all, keep looking up. The next great cosmic revelation might be just one